Okay, we'll get started. In this section, we're going to be looking at collisions. So, I'm sure you have an idea of what a collision is when objects run into each other. But in physics, it has a very specific meaning. So during a collision, objects can change their individual momenta. Momenta being, this is the plural of momentum. So again, during the collision, you can have a transfer of the momentum between different objects. So there's really two types of collisions that we're going to look at. The first one is elastic collisions. That's when objects bounce off of each other. So again, let's say we had this scenario right here. We have two objects ready to bounce in off of each, or ready to run into each other. And if there was an elastic collision that resulted, they would bounce off of each other. So this would be an elastic collision, what I'm drawing. The other thing that could happen is you have them run into each other, but instead of bouncing off of each other, they could stick together. And that would be the other type of collision. That would be an inelastic collision. So again, those are the two main types of collisions. Objects could either bounce off of each other or they could stick together. The next thing is that's important for dealing with collisions is if there are no outside forces, so outside forces being stuff like friction, air resistance, then we can assume the total amount of momentum during a collision is conserved. So again, conserved meaning remains constant. So that basically says as long as we can negate outside forces like the force of air resistance, the force of friction, we can say that the momentum in the system is really not going to change. The momentum between objects is really just going to get moved around. It's not being transferred outside of each individual object. So again, if we can say this, if we can negate outside forces, then we can really apply this. We can apply the law of the conservation of momentum. So this really nicely describes what happens to the momentum of objects during a collision. So this is how it's written. It's pretty straightforward in terms of notation. So it basically says this net pi, or sigma pi, right? This is the total initial momentum. That's the sum of all the momenta of each object before the collision. So again, let's say two objects are about to run into each other. If we added the momentum of each object, that would be the total initial momentum. And then it's saying that's equal to the sigma pf, so the total final momentum, which is the sum of the momenta after the collision. So again, if we look after the collision already happened, and maybe they bounce off, maybe they stick together, but if we look at the total momentum after the collision, that's going to be equivalent to the momentum, all the momentum before the collision. So again, what this really says is just that the momentum is going to go somewhere. Again, it's as long as we don't have to worry about any outside forces, it's going to just get moved around between the objects that are participating in the collision. And that actually is really helpful. We'll actually be able to find a lot of useful information using this. So just to quickly recap, the new idea of collisions, and there's two different types of them. And if we don't have to worry about any forces outside the collision, then we can think about the conservation of momentum, and that basically tells us that momentum's not going anywhere. It's not being created or destroyed. It's only really transferred between objects. Okay. What's going to be helpful now? We're going to go through an example problem of a collision. Okay, so what I have here is a nice example problem of the type of a collision. So you're going to see lots more of these later. So before I go through the solution, take a minute or two and get as far as you can solving it out. Okay, take an attempt at solving it. Again, not reading Reddit threads, solving. Okay, we'll get started, so I'll go through this. So the situation we have is we have a 5 kilogram red block. It's going at 10 meters a second to the right, and it runs into another block. It runs into a blue block. It's going at 7 meters a second to the left. It says the two blocks collide, and the blue block bounces off at 6 meters a second to the right after the collision. So it's asking how fast is a red block moving. So it's implying, after that collision happens. So this is what we have. We have two blocks. We have a red block. We have a blue block. The red one's going to the right. The blue one is going to the left. So I'll say this is, I'm going to just label this I, so initial, before the, all the stuff that's happening before the collision. And then it's saying they bounce off of each other. So we don't know what happens to the red exactly, but it says pretty explicitly that the blue is bouncing off to the right. Again, I'll say this is F, so this is final, so this is all the stuff that happens after the collision. So this is the idea of what we have. We know they're going towards each other, and they're bouncing off, but we don't know exactly what happens to the red. So the way we're going to do this is with the conservation of momentum. So again, we're going to say that friction and air resistance, for this simple example, really aren't too big of a concern here. So we're just going to look at the momentum of each object. So we're going to say this. We're going to write out the conservation of momentum. So again, the total momentum before the collision is equal to the total momentum after the collision. So again, we're going to write, again, momentum is the mass times the velocity of each thing. So we're going to write out all of the momentum of each object. So we're going to write it m1. So that's the mass. I'm going to write this. So again, we'll say the red just for notation. That's going to be 1. Anything with a 1 is going to refer to the red object. And blue, I'm going to call that number 2. So anything with a 2 is going to refer to the blue object, the blue block. So again, I'm going to write out the momentum of each object before and after the collision. So again, momentum being the mass times the velocity. Again, let's write this out. What's the momentum of the red block before the collision? Well, we're going to say it's m1 times the velocity, which is, say, is velocity initial, so the velocity before the collision, 1. And then that's going to be added to the momentum of the blue block, so we're going to call that m2 for the blue block, times vi2, so the initial velocity the velocity before the collision of the blue block. Then that's equivalent to all the momentum that, exists after the collision. So we're going to write in the mass 1, mass of the red block, times its velocity final, the velocity after the collision, 2, so 2 for the red, is plus the mass 2, so the mass of the blue block, times its final velocity oh, sorry, I made a small mistake. This should say VF1 instead. So this should be so again, VF1 referring to the red block. So this is going to be m2, the mass of the blue block, times the final velocity of the blue block. So again, what I did is basically I wrote out all the products of mass times the velocity of each object. So before the collision, after the collision, and now the only thing left to do is really to plug in the numbers, plug in the masses and the velocities of each object before the collision and after the collision, at least as far as we know. So again, I'm going to start to go through, I'm going to plug in, okay, what's m1? What's the mass of the red block? That would be 5. What's the initial velocity of the red block? That's going to be 10. I'm going to add that to what's the mass of the blue block? That's 3. What's the initial velocity of the blue block? That's 7. It's going to be negative 7 because it's to the left. And then that's going to be equal to, mass 1 again, so the mass of the red block, times the final velocity of the red block, which we do not know, so that's still a symbol. And then we're going to add it to m2, which is the mass of the blue block. So again, the mass of the blue block is, again, 3 kilograms times the velocity right after the collision. So it's going to be 6 meters a second, and it's positive because it's to the right now. To the right. And then the last thing we're really going to do is just solve out algebraically for this. So I'm going to solve this side is 29. Technically it's Newton seconds, but I'm going to leave the unit off. So all of this together is 29. And then it's going to be equal to 5 times the final velocity of the red block plus 18. So again, solving that out, we're going to get 11 is equal to 5 times the final velocity of the red block. So the final velocity of the red block is going to be 2.2 meters per second, which again, because it's, if we plugged everything right and in right, and we did, this positive actually indicates to the right. So it's really going to be 2.2 meters per second to the right. So again, that's the answer. 2.2 meters per second to the right. And this is really what would be happening. So we have the collision between the two, and then they're bouncing off each other, and then the red one's going to be going to the right. Again, the same direction the blue's moving. Okay, so again, that's the problem. Make sure your notes are notated, and you have the solution to this problem. So that's it for now.